Today we will study intensity of magnetization and magnetic intensity. What is the difference? For this, we will discuss Rowland ring. It is actually toroid with some material, core material. If you want to study magnetic property of a particular material, we will make a ring of this material. We have connected a battery having V volt. This one is free current because we can adjust at our will. Suppose current is this way. So magnetic field inside the ring, inside the material, this one. But if the turns are perfectly circular, there is no leakage of magnetic field. So outside magnetic field 0, here 0, field in this region only. In the absence of material, magnetic field in this region is mu naught NIF. It is the formula for the very long solenoid. IF stands for free current. But in presence of material, there will be bound current also on the surface because of atomic current loop adjust according to external magnetic field. So due to this extra magnetic field, say BB, magnetic field due to bound current, it is mu naught NIB. So net magnetic field inside the material is BF plus BB. So it is mu naught NIF plus mu naught NIB. NIB is denoted as small if, which is free current per unit length. Similarly here small ib stands for bound current per unit length. So this is the net magnetic field. Now let M1 be the magnetic dipole moment per unit length due to bound current. Suppose this length is 1 meter and small m represents the number of turns per unit length. So in 1 meter of length there are small n number of turns. So magnetic dipole moment of this part due to bound current is n times IBA. So magnetic dipole moment due to bound current per unit volume, which is called intensity of magnetization, and it is denoted as M. So what about the total magnetic dipole moment of this part? It is M1 or it is NIB into A, and the volume of this part is area of cross section into length. So if we divide M1 by volume, we get magnetic dipole moment due to bound current per unit volume, which is called intensity of magnetization. It is not magnetic dipole moment, but it is the magnetic dipole moment due to bound current per unit volume. So A cut out, so at last NIB, and it is represented as small ib. Similarly, the same quantity due to free current, it is denoted as H. That is magnetic dipole moment per unit volume due to free current. It is denoted as capital H. And experiment says that because of IB current generated due to free current, so M depends on H. M varies H. Up to certain limit, M is directly proportional to H. So if we want to remove the sign of variation, we have to put some constant, say chi m. Here chi m is called magnetic susceptibility of the given material. It depends on temperature also. So final magnetic field B is what? This one. B is mu naught H plus mu naught M. But M is chi m H. So mu naught H plus mu naught chi m H. Mu naught into 1 plus chi m into H. This term is called magnetic permeability of the given material. Mu naught into 1 plus chi m equal to mu. So mu by mu naught, it is called relative magnetic permeability. It is 1 plus chi m, and it is denoted as capital Km. Relative magnetic permeability. Now, according to magnetic property, we classify 3 categories. 1, paramagnetic, diamagnetic, and ferromagnetic. So what are paramagnetic substances? So a material is called paramagnetic if its molecules or atoms possess permanent magnetic dipole moment. that is a permanent magnetic dipole. For paramagnetic material, paramagnetic material, chi is greater than 0, but very small. If we place this is bar magnet, and suppose this one is aluminum nail. Aluminum is paramagnetic, so dipole moment is induced, but very feeble. Here N, so dipole moment is here S and N. So it is attracted towards the stronger magnetic field. For example, aluminium, sodium, calcium oxide at STP, and copper chloride are paramagnetic. If we place paramagnetic material block in uniform magnetic field, some field lines are absorbed by the material. So magnetic field inside the material is somewhat greater than uniform magnetic field. Now the diamagnetic material, the atoms or molecules do not possess permanent magnetic moment due to paired electrons. So as a whole, it is not having dipole moment, a particular molecule or atom. And for diamagnetic material, chi is less than 0. That is, if we place suppose gold nail in the magnetic field of bar magnet, this end induced as north pole and this induced as south pole, opposite to that of. So minor repulsion is there because of chi is very less, negative but very less. So poor repulsion is there. So it is moving towards the weaker magnetic field. If we place here, if we place block having diamagnetic material in a uniform magnetic field, somewhat field lines away from this. So net magnetic field inside the material somewhat less than the actual magnetic field, uniform magnetic field. For example, diamagnetic material, aurum, argentum, copper, water, bismuth, etc. Now the third category is ferromagnetic substance. Ferromagnetic substance also possesses a permanent dipole moment as an atom or molecule, but they forms domain structure also. Observe the figure. Suppose this one is iron sheet. There are domains in this domain. Magnetic moments are this way, this way, this way. But as a whole, it is neutral. No magnetic effect. No magnetic dipole moment. For ferromagnetic material, chi is double valent one. For example, iron, nickel, cobalt, etc. If we place iron nail in magnetic field of bar magnet, this one end generates as south pole and this one is north pole. So it is attracted towards, strongly attracted towards stronger magnetic field. And if we place iron block in a uniform magnetic field, most of the magnetic field line passes through, it sucks magnetic field, passes through the iron block. So inside the iron block, magnetic field becomes so stronger. Now again for paramagnetic material, magnetic dipole moment per unit volume, it is intensity of magnetization is directly proportional to magnetic field B, applied magnetic field, and inversely proportional to temperature. Combining these two, M varies B by T. So M equal to C into B by T. C is called Curie constant. But we know that M is chi m H and B is mu naught NIF, but NIF is H. So mu naught H. If we replace here, M is chi m H, C is as it is, B is mu naught H upon D. Cut. So chi m is C mu naught by T. That is chi m is directly proportional, inversely proportional to temperature. For diamagnetic material, chi m does not depend on temperature, almost. Now for ferromagnetic material, as the temperature of a ferromagnetic material is increased, the domain structure gets distorted. At a certain temperature, depending upon the material, it is totally broken up. Each and every atomic magnetic moment attains independence from one another, and the substance gets converted into a paramagnetic material. After that, chi m is given by C1 upon T minus Tc. C1 is constant and T is greater than Curie temperature. The temperature at which ferromagnetic substance is converted into a paramagnetic form is called Curie temperature of that substance. Now hysteresis cycle. Suppose this one is solenoid and we have connected a battery, and we will put material we want to study. What about the magnetic field inside the material? If current is applied, it may be any we want to study. Suppose this one is iron and this one is B versus H. B is the net magnetic field, H is the magnetic dipole moment due to free current per unit volume. If H increases, B increases, but initially it will not respond. Slowly respond, and then after, if H increases, B also increases, this way. But at certain point, at certain H, all dipoles are aligned with the magnetic dipole, external magnetic field. After that, saturation attains. So almost no increment with the increase of H. If we decrease the current in the same direction, in this case, suppose the current in this direction, this end is becomes north pole and this end south pole. But now in this direction we are decreasing the current, so B also decreases, but not traversing the same path. At last, if the current becomes zero, but the material is magnetized permanently, this one, if this length is greater magnetic field is there, permanent magnet. If we if we reverse the direction of current, initially this one, but now we are applying this current. So at certain current, net magnetic field inside the material becomes zero, and this point is called coercivity. The value of H when B equal to 0 is called coercivity. Similarly, this point is called retentivity or remanence. The value of B when H equal to 0 is called retentivity or remanence. If we further decrease the current from this point, it will attain saturation in opposite sense at certain point. And then after further decreasing the current, again we get the same, this point, retentivity remanence, but opposite to that of the original one. And again we increase this hysteresis loop. The area of this hysteresis loop gives the heat generation in the material per cycle per unit volume.